This online tutorial is about the Lewis acid-base theory. Like the Bronsted-Lowry acid-base theory, the usage of the Lewis acid-base theory is very common in chemistry. The proposal of the Lewis acid-base theory by Gilbert Lewis goes back to 1923, the same year in which Bronsted and Lowry independently proposed their Bronsted-Lowry acid-base theory. Based on the Lewis acid-base theory, an acid is a molecular entity or the corresponding chemical species capable of forming a covalent bond with a provided electron pair, and a base is a molecular entity or the corresponding chemical species capable of forming a covalent bond by providing or sharing an electron pair. In other words, a Lewis acid is an electron pair acceptor and a Lewis base is an electron pair donor. So we have the Lewis acid-base theory based on which acids are capable of accepting an electron pair. To form a covalent bond. While bases are capable of donating an electron pair to form a covalent bond. Or in fact, acids are electron pair acceptors and bases are electron pair donors. For example, consider the reaction between BF3, boron trifluoride molecule, and NH3, ammonia molecule, which yields H3N BF3, ammonia boron trifluoride. The Lewis structures of the reactants and the product in this reaction are as follows. Based on the Lewis structures, it is easy to see that in this reaction, the nitrogen atom of the ammonia molecule shares its lone electron pair with the boron atom of the boron trifluoride molecule. And the boron atom accepts that electron pair to form a covalent bond with the nitrogen atom, which yields a single reaction product, H3N BF3. So in this reaction, BF3 is accepting an electron pair. It is an electron pair acceptor, so we can consider BF3 as a Lewis acid in this reaction. On the other hand, in this reaction, NH3 is donating an electron pair. It is an electron pair donor, so in this reaction, we can consider NH3 as a Lewis base. The Lewis acid-base theory is broad and we can consider many examples here. Substances like BF3 with electron deficient atoms are good candidates as Lewis acids. In BF3, the boron atom has 6 valence electrons, which is less than the 8 valence electrons required to obey the octet rule. So here, the boron atom is an electron deficient atom, which has the tendency to accept an electron pair and in order to complete its valence shell and obey the octet rule. Therefore, it acts as a Lewis acid. While substances like BF3 with electron deficient atoms are good candidates as Lewis acids, many Lewis acids don't have any electron deficient atoms. For example, consider this reaction. SiF4 plus 2F minus yields SiF6 2 minus. In this reaction, the silicon atom of the SiF4 accepts 2 electron pairs from 2 fluoride ions and forms this. Therefore, in this reaction, SiF4 is a Lewis acid and F- is a Lewis base. The silicon atom of the SiF4 has 8 valence electrons and obeys the octet rule. Yet it can accept more electron pairs and it can act as a Lewis acid. As another example, consider this reaction. PF5 plus F minus yields PF6 minus. In this reaction, the phosphorus atom of the PF5 accepts 1 electron pair from a fluoride ion and forms PF6 minus. In this reaction, PF5 acts as a Lewis acid and F minus acts as a Lewis base. In PF5, the phosphorus atom has 8 valence electrons. It is more than the phosphorus atom has 10 valence electrons. It is more than the 8 valence electrons required to obey the octet rule. Yet, the phosphorus atom of the PF5 can still accept another electron pair. It can act as a Lewis acid. Metal cations are also good candidates as Lewis acids. For example, in aqueous solutions, a Ni2 plus cation can combine with 6 ammonia molecules to yield NiNH3 taken 6 times 2 plus. In this reaction, the Ni2 plus nickel cation accepts 6 electron pairs from 6 ammonia molecules to yield this, which is a coordination entity and studied in coordination chemistry. Like this reaction, in this reaction, Ni2 plus is a Lewis acid and ammonia molecules are Lewis bases. Like this reaction, Lewis acid-base concept plays a vital role in coordination entities and generally in coordination chemistry. Also, substances with pi electrons can act as Lewis acids. For example, consider this reaction. MgO plus CO2 yields MgCO3, magnesium carbonate. In this reaction, the oxide ion donates an electron pair to the carbon atom of the carbon dioxide and forms the carbonate ion. In this reaction, the oxide ion is a Lewis base and the carbon dioxide molecule is a Lewis acid. We can consider these Lewis structures here. In which I have omitted the spectator ions the magnesium ions. The carbon dioxide molecules have pi electrons, and they can use them to act as a Lewis acid. So we see that the Lewis acid-base theory is broad, and we can consider many examples as Lewis acids. On the other hand, we can consider many substances, or in general molecular entities, as Lewis bases. In many cases, Lewis bases like fluoride ions or ammonia molecules share their lone electron pairs. But there are also cases in which Lewis bases share pi electron pairs or even sigma electron pairs. In the context of acids and bases, acid-base reactions or reactions between acids and bases are very important. What happens at an acid-base reaction is different from one acid-base theory to another one. Based on the Lewis acid-base theory, in a reaction between a Lewis acid and a Lewis base, we have sharing of an electron pair and formation of a covalent bond. Therefore, in a Lewis acid-base reaction, we have direct combination of a Lewis acid and a Lewis base, resulting in a single reaction product. This means that a Lewis acid-base reaction is an addition reaction with the formation of a single reaction product, or an adduct, where this adduct here is called a Lewis adduct. So the general form of a Lewis acid-base reaction is as follows: Lewis acid plus Lewis base yields Lewis adduct. For example, in this reaction, as a Lewis acid-base reaction, BF3 as a Lewis acid in an addition reaction reacts with NH3 as a Lewis base to yield a single reaction product H3 and BF3 as a Lewis adduct. Here it is also important to note that in a Lewis acid-base reaction, we have coordination and formation of a coordination bond. But what is coordination? Coordination is the formation of a covalent bond whose two shared electrons have come from only one of the two parts linked by it. It is in fact the reverse of the unimolecular heterolysis. And a coordination bond is a bond formed in this way. To make this clear, consider these two reactions. Methyl radical and chlorine radical yields chloromethane. And the second reaction, methanium cation or methyl cation and chloride ion yields chloromethane. the final results of these two reactions are the same. In both of these reactions, we have the formation of the CCl covalent bond. The CCl covalent bonds formed in these two reactions are exactly the same, but they are formed in different ways. IUPAC uses the term colligation for the process in the first reaction, and the term coordination for the process in the second reaction. Both colligation and coordination are the formation of a covalent bond. But in colligation, two shared electrons have come equally from two parts. One electron is shared by the carbon atom, and another electron is shared by the chlorine atom to form the new CCl covalent bond. But in coordination, two shared electrons have come from only one of the two parts linked by it. Here, in the second reaction, the chloride ion shares the two electrons to form the new covalent bond. It is important to note that the new formed bond, the CCl bond, isn't different in final results of these reactions. The properties of the new formed bond doesn't depend on the processes by which it has been formed. The processes are different. It is also good to note that colligation is the reverse of homolysis or homolytic cleavage, and the coordination is the reverse of heterolysis. So we see that in a Lewis acid-base reaction like this, we have the coordination process and we have formation of a coordination bond. In this reaction, the coordination bond Bn is formed, whose two shared electrons have come from only one of the two parts linked by it. In this case, the nitrogen atom provides both electrons, both bonding electrons. And the boron atom hasn't brought anything. It just accepts those bonding electrons. Here, it is also good to be familiar with the terms electrophile and nucleophile. An electrophile or an electrophilic reagent is a reagent that forms a bond to its reaction partner by accepting both bonding electrons from that reaction partner. And a nucleophile or a nucleophilic reagent is a reagent that forms a bond to its reaction partner, to an electrophile, by donating both bonding electrons to that reaction partner. We see that we see here we have similarities between definitions of electrophile and Lewis acid, and also between definitions of Lewis base and nucleophile. Because of this, sometimes we can use these terms instead of each other. For example, electrophilic reagents are Lewis acids and nucleophilic reagents are Lewis bases. But there are also differences in their usage. IUPAC considers electrophile and nucleophile as reagents with some specific properties. In older literature, reagent is used as reactant, but in more specialized sense, IUPAC considers the term reagent as a test substance added to a system to bring about a reaction or to see whether a reaction happens or not. Also, there are differences in the associate terms of these terms. For example, Lewis acidity is a term to show the tendency of a substance to act as a Lewis acid. It is related to thermodynamics and it is measured in the terms of relative equilibrium constants. On the other hand, electrophilicity is a term to show the relative reactivity of an electrophile. It is related to kinematics and it is measured in the terms of the relative rate constants. It is good to be familiar with these terms and it is also good to consider that although sometimes these terms are used instead of these terms, it is better to not consider them equivalent with each other. Here, it is also good to be familiar with the related terms that are considered to be obsolete by IUPAC. IUPAC, this discussion is based on the IUPAC's Gold Book version 2.3.3. which is a book for the chemical terminology by IUPAC. For example, IUPAC considers the term electron acceptor and also the term electron donor as obsolete synonyms for Lewis acids and bases. IUPAC considers the term electron acceptor as a term for a molecular entity to which an electron may be transferred. And IUPAC considers the term electron donor as a term for a molecular entity which can donate an electron, which can transfer an electron. IUPAC considers these terms as obsolete synonyms for Lewis acids and bases. So we see here that the word pair is very important here. We can use electron pair acceptor instead of Lewis acid, but we can't use electron acceptor instead of Lewis acid. Also, we can use electron pair donor as a synonym for Lewis space, but we can do this with electron donor. The word pair here is essential. Also, IUPAC discourages the usage of the terms coordinate, link, and coordinate covalence. Instead of coordination bond. These two terms are considered to be obsolete, and instead of coordination bond, we shouldn't use them. Based on the IUPAC Gold Book, we should also be cautious about the usage of the common term dative bond. IUPAC considers a dative bond as a coordination bond whose heterolysis requires less energy than its homolysis. We can break bonds in two different ways. For example, consider the AB covalent bond One way could be this, and another way could be like this. The value of charges are immaterial here, so the value of charges haven't been specified. In the first case, each of two participants in the covalent bond keeps half of the shared electrons, while in the second case, each of two participants in the covalent bond, one of the participants in the covalent bond keeps all of the shared electrons. This is called homolysis or homolytic cleavage. And the second one is called heterolysis or heterolytic cleavage. Based on our previous talks, homolysis is the reverse of the colligation and the heterolysis is the reverse of the coordination. Usually, homolysis requires less energy than heterolysis to break a covalent bond. But in some cases, heterolysis requires less energy. Those cases for coordination bonds are considered as dative bonds. For example, consider these two reactions. In both of these reactions, we have coordination, the formation of the covalent bond whose two shared electrons have come from only one of the two parts left by it. In the first reaction, we have the formation of the CCl covalent bond, and in the second reaction, we have the formation of the Bn covalent bond. Both of these bonds can be considered here as coordination bonds. But these bonds have different characteristics. In the case of the CCl bond here, homolysis requires less energy to break the bond than the heterolysis. While on the other hand, in the case of the BN bond here, heterolysis requires less energy. So this coordination bond can also be considered as a dative bond. But this is not true for the CCl bond here. So we see that IUPAC considers the term dative bond as a term for coordination bonds with some specific features. The distinctive feature is the fact that for dative bonds, heterolysis requires less energy to break the bond than homolysis. Also, dative bonds are usually characterized by significant polarity, lesser strength, and greater length. IUPAC considers this difference between the dative bond and the coordination bond. But it is very common in chemistry literature to use dative bond sometimes instead of coordination bond. But it is better to respect terminology by IUPAC. This is the end of this tutorial. I hope you find it useful.